Vidya, I guess, yeah, from UIC, and she was talking about signatures of dispersing Majorana modes in a proximatized topological material. So,
Okay, thanks a lot. Thanks, Ming, and the organizers for inviting me. It's been a very interesting series of talks and discussions. I was there last night when people were talking about all the different bands crossing the Fermi energy. And I'm going to show you some band structure, but I have to dissemble right now. I'm not going to attribute any of the bands to any of the orbitals because I'm not actually sure of the orbital assignment after listening to all these talks. Okay, with that, let me just go forward. So actually, I'm going to deviate from many of the talks that have been about correlations. And the previous talk was about wild points, and here I'm mostly going to talk about some topological aspects in this material. Um, so a lot of the STM work I'm going to show you today was carried out by my former postdoc, Zhenyi Wang, who's actually a faculty in China right now, with the help of graduate student George Rodriguez. And I suspect I won't get to this, but if I do get to this, I'd like to show you some monolayer FE-SET films that we've grown on bismuth telluride. And this is really intriguing because these monolayer films behave exactly like the bulk compounds. And there's a lot of interesting physics there, but I have a feeling I might not get to it. In any case, that work was done by my graduate students, Guanan Chen and Anuba Aishwarya. We had a lot of theory help from Taylor Hughes and Dirk Moore. And the single crystals of FeSCT I'm going to show you today in today's talk, we got from Genda Gu's group in Brookhaven. So essentially, this talk is about this particular idea, which was proposed by Charlie Kane and Liang Fu in 2008, which is that if you could take a topological insulator and proximitize it with a superconductor, then it's a great platform to realize different kinds of Majorana states. So for example, in such a system, if you could turn on a magnetic field, then you would expect to see inside the vortex cores in the proximatized topological insulator, you should see zero bias Majorana bound states. Also, if you have, by some clever engineering, if you could put two superconductors with a pi phase shift, or in fact, as it turns out, any phase shift on top of this topological insulator, then at the boundary between these superconductors with different phases, you expect to see propagating Majorana fermions. So the signatures of these vortex-bound states would be seen, for example, in STM spectroscopy as a zero bias peak inside the superconducting gap. And if you were to achieve this geometry where you have this a phase shift between two superconducting regions, then at the boundary, you should see dispersing Majorana states. And these Majorana states should be helical states, and they should have linear dispersion. So in today's talk, I'm going to show you STM data from my group as well as other groups. And I think what I really want to say is that if you just take one data set by itself, it's not very convincing. But if you add all the pieces of information together, then it seems pretty certain now that we are able to realize Majorana modes in these kinds of proximatized systems. So in 2015, there was this idea, this proposal that FeSET has in fact one band that is inverted at the gamma point. And because of that, it's topologically non-trivial. And due to its topologically non-trivial nature, it has topological surface states. So the beauty of this, of course, is that since this is a superconductor, you have this kind of an intrinsic proximatized superconductor where the topological surface states become superconducting by proximity effect. And now you have in one system this ability to realize Majorana fermions. So this is the phase diagram, and you're all very familiar with it. I'm not sure how big this box is supposed to be, but somewhere around this composition is where this band inversion is expected to happen, around 50-50. And so this is what I was telling you at the beginning of the talk. So here's a very superficial band structure. All I want to point out here is in these compounds, at least in the 50-50 compound, what you expect to see is two whole bands at the gamma point, and two very closely related electron pockets near the M point. So for convenience, we'll just call the whole pockets alpha and beta, and the electron pocket gamma. So basically, you have these band crossings. And as I said before, I don't want to assign any orbital character. Maybe we can have a longer discussion about the orbital character of these things. But what really is expected to happen is that as you go from any of the N members, FESE or FETE, to the middle, this P band and D band, they come closer. And once they meet each other and reopen a gap, that's when you have band inversion. And that happens for some range of compositions in this compound. But because of this band inversion right here at the gamma point, you expect to see topological surface states. And that's what Hongding and Shixin showed in 2018. They did ARPES, and what they could see is linearly dispersing states inside in this sort of narrow region right here near the Fermi energy. So now let's actually see some STM data. We have multiple STMs in my group. All of this work that I'm going to show you from my group at least was done in the commercial system, bought from Unisoku in Japan. And it can go to 300 millikelvin, and it has 11 Tesla field. Okay, so this is the crystal structure. You're all very familiar. One thing I do want to point out is that the top selenium atoms and the bottom selenium atoms are shifted from one another. And in STM, of course, you only see the top selenium atoms, which I have marked in orange here. And one thing to notice here is that this is the position of the bottom selenium atom. And it's if you think of this as your just a tentative unit cell, then this thing is shifted by half a unit cell, right? So this crystal structure has this propensity to have domains where, in some region, this might be the top selenium atom, but then there might be other regions nearby where this thing simply flips. So what you'll see is a domain wall with a half unit cell shift, and that's going to be important later on. So these are really beautiful samples that we got from Gendagu. This is a large area topography. And if you zoom in, you can see the selenium, and this is, a mixed compound, FESET. So you see bright and dark spots, and then so this is almost 50-50 selenium and tellurium. The reason I say that this is a very beautiful single crystal is that, a lot of these FESETE materials are plagued by excess ion. And the problem with having excess ion is it actually suppresses the superconducting gap. And you could anneal the samples to get rid of excess ion. But in this case, as it turns out, these samples that I'm showing you, you can see this in this large field of view. This is maybe just one little excess ion, or maybe this one here, that's it. We didn't have to anneal these samples. And because of the quality of these crystals, what you can see very nicely when you take STM data is a beautiful superconducting gap with a very flat density of states. Now, this here is a line cut. It shows you spectra taken along this line. And what you see immediately is A, there are multiple coherence peaks, right? You can see one here, and so on. And B, these coherence peaks actually shift around as a function of position. So it's obviously electronically inhomogeneous, and there are multiple gaps. And these multiple gaps come from these various pockets that I was talking about earlier that cross the Fermi energy. And if you take data from specific heat, RPES, optical conductivity, etc., and you put it all together, basically you find that in a sense, you should see, you have these two hole pockets are expected to have a gap of approximately 1.5 MeV and 2.5 MeV. And what I talked about earlier, which is the topological surface state, is expected to have a gap of 1.8 MeV. So leaving aside this larger gap, if you look at the, the energy range between 1 and 3 millivolts, what you should see with STM is actually 3 distinct coherence peaks associated with these 3 bands, 2 of which are the bulk bands, and 1 of which, this one, is the surface state. So let's ask if we actually see this. And so we can go and measure the gap at each position. And as usual, we can, this is what I would call a gap map. But the most important thing here is that there are regions here where you see 3 distinct gaps. And if I do a gap histogram, this is a statistical analysis from, thousands and thousands of spectra, then you can see that we do have 3 distinct gaps, although the histograms, this is because of inhomogeneity. With mean values, the gap values have mean values of 1.3, 1.8, and 2.4 MeV. The reason this is important is because then you can compare to RPES and you can assign, that this particular low energy gap at 1.3 MeV is the alpha pocket. This is the topological surface state, and this is the beta pocket. I'm showing you all this basically to establish that these samples, this is very consistent across RPES and STM. Okay, so now we can turn on a magnetic field and look for these Majorana bound states. And so here's a DIDV map showing vortices. You can almost see a hexagonal arrangement of the vortices here. And if you look at one of these vortices, take a line cut across it, here's what you see. Here's the superconducting gap far away. And right at the center of the vortex core, you see a nice sharp peak in the density of states that's at 0 energy. Now, the first people to look at vortices in this system were Hong Ding and, sorry about that, Hong Jun Gao. They did some really nice work showing for the first time that you see this zero bias vortex in this material. The problem is that at the beginning, when this work was done around 2018, they found that only a small fraction of the vortices would show these zero bias states. So there was that problem. And then one can ask, okay, you can see zero bias states. You actually see zero bias vortex core states even in niobium diselenide. The question is, what is the proof that these are actually Majorana bound states? In fact, one knows that you should see Carrello-Dijon metricon bound states, which are just regular bound states inside a vortex core, even for an ordinary superconductor. Now you can ask the question, how do you distinguish these Carrello-Dijon metricon bound states from Majorana bound states? And the answer is that the energy of these trivial vortex core states is given by this, where delta is the superconducting gap and this is the Fermi energy. Now, if you think about the surface state of that we see in FESCT, the Fermi energy is less than 10 millivolts, and the superconducting gap is around 1.5 MeV. And if you plug these numbers in, you realize that the trivial bound states should have energy scales of about 100 microvolts, which is actually pretty large for STM at low temperatures. So this is work done by Hanaguri's group. This is really beautiful, detailed work. And he shows many things quite clearly. One of the things he could do, because he could go to really low temperatures, is he could show that the there are zero bias bound states which are well within the energy, the energy resolution is good enough to say that these are well within this 100 microvolts. In fact, they're probably, exactly centered at the Fermi energy. So that's pretty good proof that these are Majorana bound states. Interestingly, if you're interested in this vortex work, you can also see that what he shows is that if you go to very low magnetic fields, a much larger percentage of the vortices show zero bias states. And as you increase the magnetic field, the number of zero bias states actually goes down quite dramatically. More recently, Hongding and Hongjunga have done actually two important pieces of work on these vortex bound states. One is that they've shown that you can have, unlike the trivial Caroline-metric on Dijon states, you can have vortices where you have integer spacing between the vortex bound states, and this is consistent with this being Majorana fermions. Another thing they showed is that you can show that the DIDV saturates to a value of E squared over H only for these zero bias states and not for the trivial states. And so all of this together suggests pretty strongly that one can see, these zero bias states seen in FESCTE are in fact Majorana modes. Now, in my lab, when we started looking at FESCTE, we were interested in, this was a while ago that we were interested in this. And at that point, there was, these pieces of evidence were not there. So we were very interested in asking the question, can we find any other evidence that this material is topologically non-trivial? So one thing you can do is look for signatures of these propagating Majorana states. And we have superconductivity. We know this is topologically non-trivial, at least now we do. I think there's enough evidence. The third ingredient you need is a pi phase shift. So as it turns out, this FESCTE is really intriguing because Jianping Hu wrote a paper in 2013 where he showed that if you consider all the important interactions, nearest neighbor, next nearest neighbor, and so on, then what you find is a very interesting kind of superconductor where, so this is one of the layers. This could be Fe arsenic and arsenic, or iron selenium selenium. But in any case, what you find is that the sign of the order parameter switches from the top to the bottom layer. So there's a pi phase shift in the sign of the order parameter between the top and the bottom selenium or arsenic layers. So this would be very hard to probe unless you looked at a monolayer. However, one interesting thing about this idea is that if you could find a sort of a domain wall in the system where the top and bottom seleniums are flipped, and this is what I was talking about at the beginning of the talk, you should actually expect to see these kinds of domain walls. Then you naturally have a pi phase shift in the superconducting order parameter. So here's the idea. So this is the top view on one side of the domain wall. These are the top selenium atoms. And then on the other side of the domain wall, the crystal has simply flipped over. So then what you expect to see is a half unit cell shift of the top atoms. So these, you see, this is the top atoms here, and these are the top atoms here. This is the domain wall. So you expect to see a half unit cell shift. And if you can find such a domain wall, then at least theoretically, you have all the ingredients necessary to realize propagating Majorana fermions. So, the samples normally look like this. You don't see any signs of domain walls, but if you search around, you can also see regions like this, where you have these long lines. And not all of these lines are domain walls, but if you search around long enough, then you can find the right kind of domain wall that we're looking for. So one thing is you take a region, a topography like this, and you do a Fourier transform, you immediately see that, if you zoom in here, This is the atomic lattice. And the fact is that you have these two dots. The presence of a split peak in the Fourier transform indicates that these two sides are actually two different domains. It doesn't tell you there's a pi phase shift. To see that the atoms are shifted by half a unit cell, you have to zoom in, and you can either track the atoms with by drawing lines, which is a pretty crude technique. But we've also done a more serious analysis using the phase and the Fourier transform. But essentially, whatever method you use, you can show that the atoms on the left side of this domain wall are shifted from the atoms on the right side of the domain wall by exactly half a unit cell. So this is exactly the kind of domain wall we're interested in. So then now we can ask, what do we see when we go to such a domain wall? And so here's what we see. So far away from the domain wall, we see a nice superconducting gap with actually zero density of states. And if you go to the domain wall, you see the gap, but then you see this flat density of states inside the superconducting gap. So the superconducting gap is filled up. You have a finite density of states, but it's a flat density of states. So so here is more data. So this is a line cut, which goes this way and then this way. So when you go in this direction, you see the nice superconducting gap, meaning the density of states is suppressed. And when you go along the domain wall, you see very featureless density of states inside the superconducting gap. Then you can actually increase temperature and make sure that this feature is associated with superconductivity. So this is on the domain wall. This is the spectrum on the domain wall showing the finite density of states. And if you go to high temperatures, which is 14 Kelvin above TC, this entire feature disappears. Okay, so why do you get this flat density of states? Actually, the answer is quite simple. What is predicted in the system is that you should see linearly dispersing helical states inside the superconducting gap. And if you ask what is the density of states of a one-dimensional linearly dispersing mode, it's constant. So that's exactly why you see this constant density of states. So this constant density of states represents a linearly dispersing mode living inside the superconducting gap. And then you can do other checks. This is just one example of a check. So you can take density of states maps as a function of energy. So right at zero bias, this is the domain wall. You can see that at zero bias, you have a nicely confined state living exactly in the region of the domain wall. As you increase energy, the width of the state, the spatial extent actually increases. And by the time you get to 1 millivolt, it's actually spanned, it basically fills up the entire field of view. So this is exactly what you would expect for a topological state, because for a topological state, what you expect is that you should see states at all energies inside the gap, but the spatial extent of the state should increase as you get further and further away from zero. Okay, so I think that, so these are the two things I wanted to show you. There's been a lot of work done by many different groups showing zero bias bound states inside vortex cores in this compound. And what we've shown is that if you find the right kind of domain wall in the system, you can get propagating Majorana modes. So I'm just going to, since I started late, Ming, how much time do I have? Another 5 minutes?
Well, yeah, go ahead. Maybe not 5 minutes, but yeah, it's obviously off the time, but I think, yeah, you can.
Right. No, when did I start? Okay, I don't know when I started. Shall I
Go ahead.
just flash some slides? I just wanted to flash a couple of slides and then
Great, yeah, go ahead.
Okay, so just want to show you something really interesting. This was Jianping Hu's prediction that if you have, for these ion-based compounds, we know there's a lot of evidence that we have an S plus minus order parameter, where the order parameter has a phase shift between the electron and the hole pockets. But if what he predicts is correct, which is what we based our analysis on, you also expect to see a pi phase shift between the two hole pockets at the gamma point. So we wanted to try to grow monolayers of FeSET on bismuth selenide for various reasons. And, I don't know if I'm going to have time to go through this whole thing, but let me just show you a few slides because this is very interesting. So we used our MBE system to grow FeSETE on bismuth telluride. So here's bismuth telluride, right? And here's FeSETE. And so you can see very clearly, so this is the hexagonal lattice associated with bismuth telluride. And this is one monolayer of FeSET. Now, this is pretty crazy. You don't know if this is superconducting at all. If it is superconducting, you don't know what the TC is, etc. But I'll show you that this thing is indeed superconducting. Let me skip all this. So, okay. So this is the FeSET layer. This is bismuth telluride. And if you go in here and take a series of spectra, this is what it looks like. The important thing here to notice is that this gap looks exactly like the gap we saw in the bulk compound. By the way, this topography should remind you of the bulk compound. You see 3 distinct gaps with if some regions have very nice sharp coherence peaks. But the most important thing is that the density of states is actually complete, like 0 inside the superconducting gap. So this monolayer of FeSET on bismuth telluride is a very, very good superconductor. And the TC is very similar to the bulk. So, by 13 Kelvin, that's when the gap completely disappears. You can see this proximity effect. The proximity effect is really interesting. This is bismuth telluride. And what you see is that you see a shallow gap on bismuth telluride. Remember, this is lateral proximity effect. So one imagines that only the surface state is getting proximitized. There's also the gap magnitude is pretty small compared to the gap magnitude on FeSET. But in the interest of time, I'm going to skip over all this and just show you one interesting thing, which is that with STM, you can do a phase analysis and you can ask the question, what is the relative phase of the autoparameter in these various pockets? And by doing this phase analysis, what we found is that not only is there a phase shift between the hole pockets and the electron pockets, but there's also a relative phase shift between the two hole pockets at the gamma point, which is very much in line with Jianping-Hu's prediction. Okay, I'm going to just stop here because I think I've run out of time. Thank you for your attention.
Thank you very much, Vidya, for this very intriguing talk. Any questions from the audience?
Shall I stop sharing or shall I keep sharing?
I think sharing is okay. So we have a question from Andrei Nevdomsky. Andrei, do you want to ask your question?
Yeah, sure. Hi, Vidya. Thanks for a very, very nice talk. I had a question about maybe the last part of the talk. Could you reflect on what you just told us about this relative sign change and the proposal that if you have a FeSE, this S plus minus superconducting this material, then our proposal this might actually be a higher order topological superconductor. So if you imagine making like a parallel pipette out of it, like you just think of a cube, then the gapless modes would naturally exist on the hinges of this cube. And so Nick Butch, for instance, took it as far as to then try to create a sort of nanolithographic device and measure the DIDV. And the statement or the claim is that the zero bias peak that he sees is exactly coming from these hinge modes that live sort of on the edge, if you see my hand, sort of on the edge of the two faces of the cube. So is this in any way related to Jianping-Hu's proposal and the kind of features you are looking for?
So there are two things. One is okay, so yeah, I know what you're talking about. let me think for 1 second. So the John-Pick-Hughes idea that if you take into account all the nearest neighbor, next nearest neighbor hoppings, etc., that it's this so-called effectively an odd parity superconductor. Can you see my screen?
Not a full screen, but we can see it. Yeah.
Yeah, okay. So this is John-Pick-Hughes' proposal. I think this is consistent with the existence of hinge modes. If you have a 90-degree, if you have a sort of a crystal facet, this going this way and this way, I think this would also give you edge modes, actually. Yeah.
Well, just to be clear, Jinping-Hu's proposal is about the right-hand side, not the left-hand side of the figure, right? I think the left-hand side is just for comparison. What would happen in, like, putative P-wave superconductor?
No, actually,
No?
the left is John-Pick-Hughes' proposal.
Oh, I
And
see.
the
So
right
he's
is what, so this is what he's proposing. This is, I couldn't change this. This is directly taken from his talk, but I would have put quotes around the odd parity. So this is an effective odd parity superconductor is what he's proposing. Not just FeSET, depending upon the circumstances. He's saying many of the pnictide compounds could be in this particular state, where if you do realize this kind of effective odd parity superconductor, then the proposal would be that not only do you have a sign change in the order parameter between the hole and the electron pockets, as shown here on the right, but you also have a sign change between the two hole pockets themselves. And this also is the reason that you would then, let me see, this is the same idea that where you have the superconducting order parameter then having, having the top layer and the bottom layer also show, in real space, also show a phase shift. So those two things go hand in hand.
I see. Very good.
Thank you. And next question, Amir.
Yeah, thank you very much for your very nice talk. I have a question regarding the growth of this iron selenium tellurium 50/50. You said that you can grow these materials without interstitials or iron excess.
Yeah.
And yeah, I find it a bit strange because that material actually allows iron excess in the lattice, and normally the people, they anneal the samples, and still if you anneal it, it's not guaranteed that it's not 100% of
You're absolutely
the
right.
iron, exactly, the excess of iron. So I'm puzzled by the fact of, also from the phase diagram point of view, it's a little bit surprising to me that one can access it. I mean,
there's a reason. I can tell you the reason.
Yeah, go ahead.
Okay, the reason is the way we grow it. It's iron deficient in some ways. So what we do is it's a clever technique, actually. We didn't invent this. You put iron on top of bismuth telluride, okay? And just iron, right? And you anneal it in a selenium atmosphere. And so all the iron that exists on top, it binds to either selenium or tellurium. That's why you end up with no excess iron. So the way you grow this is not what you're not growing it by evaporating Fe, Se, and Te. Instead, we're depositing only iron on top of bismuth telluride, and then annealing in a selenium-rich atmosphere, and that's it. And that's what gives you this. So the proof of the pudding, I mean, the thing is that you do that, and this is what you end up with. You don't end up with any excess iron. It's really nice.
Okay, thank you very much.
Sure.
And last question, Simel.
Yeah, Vidya, a beautiful talk. So I actually have a question which maybe more is for ARPAS groups, but in a spirit of discussion.
Yeah.
How much of the evidence that there actually is for the band inversion in a bulk?
Yeah, okay. This is very tricky. So when this paper was first published, Hongding's paper, I think there was a lot of controversy. I'm not sure everyone believed it. And we ourselves were extremely skeptical. And the one reason that I wanted to actually study this compound was because I wasn't convinced at all by this RPAS. However, there are two things. One is, I think multiple groups have seen these surface states now. So there's that. And you can show that they're surface states because, there's no KZ dispersion. Moreover, I think that's what I meant by accumulating data. I think that given all the beautiful work done by Hongding, Hongjun Gao, and Hanaguri, showing that these Majorana bound states exist inside the vortex cores in these compounds, you might think of it as indirect evidence. But I think that without a topological surface state, that would not happen. So just working backwards, you have Majorana bound states. That requires a topological surface state, which in turn requires band inversion at an odd number of points inside the Brillouin zone. So that's my answer.
No, that's fair. But on the other hand, this is a material which has been looked at from a variety of perspectives, including from correlation physics and etc. So there's a lot of ARPAS data that probes the bulk spectrum. And I just wonder whether anybody has really directly seen the inversion of the P and D bands in the bulk.
You want to do this as a function of doping, I presume?
No, just 50-50. And
if I may comment, this was just done. I posted the link to the archive paper. So there is a appearance of the topological surface state as a function of tellurium concentration and disappearance of superconductivity.
No, but I'm asking about a bulk, not a surface state.
Yeah, in the there is appearance of a surface state which is indicative of a band inversion in the bulk. And that's as a function of tellurium, and actually happens not at 50%, but around 55.
Yeah.
So there is a phase diagram that has been recently established of topological superconductivity, non-topological superconductivity, and in fact, the non-superconducting state at the excess of iron, which begins roughly at a stoichiometric composition of iron 1. So this phase diagram is basically similar to the famous phase diagram of correlated materials in strong spin orbit regime. So X, the iron composition, quantifies the correlation effect, and Y, the tellurium composition, quantifies the strong spin orbit coupling effect. So in any case, what I wanted to mention is that in the real material, of course, you have fluctuations of composition. So there are regions from different parts of that phase diagram. And the reason that people have observed topological and non-topological vortices at the same time on the surface of the same sample is because these Gander samples, which are 0.45, 0.55, are nearly exactly at the boundary of the non-topological to topological superconductivity transition.
So I can pull up the paper, but I don't think we have time.
Yeah.
What is the...
That's it. I mean, you can look it up. The figure 4 shows the phase diagram I was talking about.
Okay, all right.
Sounds like this would be a good time.
I think we should probably stop on this point. But the point is that at least according to DFT, the band inversion is actually happening above the Fermi energy. So I don't know how ARPAS can actually see it.
Sounds like it's a topic we can follow up with the discussion.
No, that's true. So that there is that problem. Maybe I should stop talking because Ming wants me to, but there is that problem. Band inversion is not happening. Yeah, band inversion is happening at a different point in KZ. That's true. That's why you can only see it indirectly. If a surface state suddenly appears and it has sort of linear dispersion, then you have to ask, why is there a surface state now suddenly at this composition?
Thank you, Vidya.
So the surface state, I think various ARPAS group have seen with laser ARPAS where you have the resolution to see the surface state. But I guess the question is, can you do this with KZ dependence at a synchrotron? And that's something I think a number of groups are working on. Perhaps that will contribute to this discussion.
Okay, I'm going to stop sharing.
Thank you very much, Vidya, for this very interesting discussion. Maybe we can follow up in the discussion tomorrow, since we have one more talk by Ziqiang Wang from Boston College. Ziqiang, do you want to start sharing your screen? Are you there?
Okay, yeah, I'm here. Can you see the screen?
Yes. You want to try to share? Perfect.
Oh,
yeah.
okay. All right.